So with this presentation, indeed, I'm going to talk about damage detection in thick composite via infrared thermography and transfer learning. I would like to acknowledge my co-authors from TU Eindhoven and from TU Delft, and that within the context of our research project, indeed, we performed this analysis together. The framework of the, let's say, the bigger picture is damage detection in wind turbine blades, which is mostly carried out by visual inspections, and it's very time consuming, and it involves stopping the wind farm or some wind turbines in order for the inspection to be performed. So there is quite some downtime associated with it, and visual inspection is only able to, in the end, detect surface damage like leading edge erosion or trailing edge cracks. But in this case, in these structures, we can also have some internal defects, which will not be inspectable by visual inspection. So the idea is to employ infrared thermography. Well, that is not very novel. It has been used quite sometimes in the literature, but to couple it with artificial intelligence in order to have, in the end, an idea of the health status of the blade. So the problem is that there is a strong lack of training data from real blades. Well, also this work is not concerning actually real blades, as you will see. And that the detection for deep defects is very much difficult also with infrared thermography in general. So in order to more or less tackle these challenges, we make use of transfer learning that you have seen also in the previous presentation. So we use a pre-trained model, and this type of learning is, in the end, it's a type of training, more or less mirrors human learning, right? When you know something, when you know how to do something, learning related stuff is a little bit easier than if you start from scratch. So in the end, this results in a reduction of amount of data required to learn specific tasks. This can be summarized more or less with this image, where we have a pre-training stage in which we have essentially, well, in relation to what we are doing, we are using simulation data to train a deep learning model. We will see that later. It's a convolutional neural network for image segmentation. And then we learn, we teach, essentially, the neural network gets calibrated, all the parameters are trained in order to perform a specific task, which in this case is damage detection. In the second stage of learning, we use the few experimental data in order to train only the deep layers of the latest layers, last layers of neural network, in order to improve the applicability of the previously trained neural network to detection in actual real data and not simulation. So we have a few, this is basically our data set. We perform step-heating thermography on one composite plate, which is in the end the material we want to perform damage detection with, and 4 epoxy resin plates. And then instead we performed also, in addition, some simulations on well, by considering epoxy resin plates. So the model, the finite element model, has been calibrated to represent the same epoxy resin plates, and then has been used to generate a synthetic data set of many types of, including different types of defects and distractors. Then we use a principal component thermography, which is essentially a pre-processing step in order to synthesize the video in a few images. So we transform the temporal let's say the temporal images, the temporal sequence into a few stacked images, ending up in the end in a 3D array. And these results, given the number of experiments that we did with each and every set of specimens, we end up with 7 data actually for the composite plate, 28 for the resin plates, 4 simulation for the same resin, and almost 1,000 simulation considering the variation of defects and so on. Then we use these experiments to train 2 UNet. We'll see that in a moment. It's a typical neural network that is used for image segmentation, and to define 2 benchmark models. So a benchmark model that has been that has only seen composite, let's say, measurements conducted on the composite plate, and another model that has only seen measurements on the resin plate. And we also train the neural network only with our simulation data, and then use this one, let's say, in a transfer learning framework, in order to retrain this model with the few experiments. So in the end, we come up with 3 neural network of which we want to compare the performance. This is the setup for the step heating thermography. So we have 3 lamps and an infrared camera. You see here the plates. The defects are on the opposite side of the plate, so they are just flat bottom holes that somehow represent the discontinuity into the material. So we conducted a fixed step heating thermography experiment by powering up the lights selectively for 5 minutes, and then let the plate cool down. Or along this time, we were recording video with the infrared camera. We end up with 7 heating conditions because, yeah, you can imagine we turn on only one lamp at a time, or a combination of 2, or all 3 of them together, resulting in different inputs. This is the composite plate that we use. It's from a previous study. Colleagues from TU Delft, we borrowed it. You can see here there are defects of different sizes and depth that is a little bit less obvious. There are defects of higher depths on this location, and they are more close to the surface, to the bottom surface, to the back surface around on the right-hand side of the plate. You see here a schematic of the defect. So we talk about defect depth. When the depth is smaller, it means that the defect is closer to the surface that has been analyzed. Then we made some epoxy resin plates with different defect shapes and depths again. So we have a little bit more variety for the epoxy material. And then this is a schematic of the finite element model that we produce. Well, within this model, it's just a transient thermal analysis with essentially mimicking the step heating thermography experiment, which we have different defects of different depth, which are randomized. So in each and every simulation, you will find a different configuration of defects. And there are also some distractors. That was something that was missing in our initial experimental dataset. Well, essentially, it can be that in real structures, actually, if you take a wind turbine blade as a web, that also would somehow introduce a sort of discontinuity into the temperature field. So we in the finite element model, we try to include some other elements as a distractor. So we consider variation in defect size, location, shape, depth, and heat flux, as well as we did essentially in the experiment. Now, when we monitor, when we extract the temperature data from the bottom surface of this plate, we essentially, since we're doing a finite element analysis, we have nodal temperature values, but we need to mimic infrared thermography because, as you can imagine, if it's different if we increase the resolution of our infrared camera. So we essentially use the same resolution. We considered the same resolution of the infrared camera by averaging nodal values and mimic in the end the pixel values. So in the end, we end up with the final image, actually a video, like for the infrared experiment, on which we perform a principal and component analysis. So we have our infrared video, we perform a principal component thermography for feature extraction, and we extract the first 9 principal components, which are 9 images in the end that we stack together, coming up with the 3-dimensional array. These are fed into a UNet type of neural network. It's a deep convolutional neural network used for image segmentation, in which each and every pixel in the end is associated to a defective or non-defective class. Well, into this encoder part of the network, essentially we have the feature extraction. And in here we have the expansion that allows us to identify whether a defect is defective or not. The skip connectors allow for bringing in the information from the higher layer when expanding the images. So in the end, this is our all our data for our resin simulation dataset, composite, and resin experiments. We have a training, validation, and test dataset for a total images that is reported in the table. One thing to notice is that training and validation data, I mean, given this very small amount of data for the composite and resin experiments, we don't exactly distinguish the training and the validation dataset, but in each iteration, we are going to take out some data for validation and some for testing, more or less in the same ratio that we have here, 1:4. In order to quantify the performance of the neural network, we use a typical evaluation metrics, which are F1 score and intersection over union. They are very similar, but use both differently sometimes, so we use both. Essentially, they are based on the for a certain pixel on the difference between the prediction and actual class. So we have true positive, false positive, false negative, and true negative. So by essentially considering the intersection between these classes, we come out with the matrix of precision and recall that allow us to calculate intersection over union and F1 score. This is a slide giving you an idea of how much the simulation was in agreement with the experiment. The only thing we had to add to simulation was synthetic noise in order to, let's say, we had to add synthetic noise to the simulation. Sorry, it's a bit distracting. You can see here the results on the pre-trained model. So simulation data tested on simulation. You can see that essentially, as expected, given the very high number of data set of data and also the low level of noise, essentially the prediction is almost perfect, right? This is the input image, the input image. You see here the ground truth and the prediction. So basically all defects are detected, and we reach almost an F1 score of 0.9, which is very high. Instead, here you see the performance of our benchmark dataset. It seems that everything is going right, but there is a lack of detection for deep defects. for both the composite plate, where we have very, very few data, but also for the resin plate, where the number of data was a little bit higher. Shallower defects are predicted pretty nicely, but deeper defects are not so well identified. F1 score reaches this metric 0.76 and 0.83. When applying transfer learning, we see a modest change in the F1 score. It's not the greatest thing. Also, even if in this field they kill each other for a few percentages, but the nicest thing is that after applying transfer learning, we increase, at least for the resin, sorry, we increase for both data set the detectability of, so this is the result of the retrained model, and this is the result of the benchmark model that I showed you before for the composite plates. We increase the detectability of deeper defects, which is, so we don't see a huge increase in the F1 score because that concerns all defects. But if we would come up with an F1 score only for deeper defects, we will see a very big change. So to go to the conclusion, we employed this methodology in which we use simulation data to pre-train a neural network for damage detection, recognizing that there are some fundamental features which are shared between the simulation data set and experiments. The transfer learning approach increase the performance of the neural network, especially for the detection of deeper defects. And these are in fact the main advantage of transfer learning in this case. We have a few points of which we want to work on, because in our simulation we use a uniform heat flux. In our experiments, the heat flux was not uniform over the entire surface. That led to a slight difference in the first principal component. So we're going to adapt this using in simulations also, let's say simulation that mimic the experiments a little bit more closely in order to have better performance, and also explore the use of more sophisticated models than the UNet, because UNet is really, let's say, the entry level in image classification problems. Thank you very much for your attention.